Okay, so in this section, what we are doing is combining what we already know about stoichiometry with what we now know about gases. So if we remember this stoichiometry map, right, it told us that whatever we were given, if we were given number of atoms or molecules of a compound, if we were given mass of a compound, if we were given volume of a gas at STP, or volume of a solid or liquid, we could, through one or two parentheses, figure out moles of one reactant or product, and then using the coefficients from the balanced chemical equation, find the moles of the other reactant or product, and then use, our molar mass, Avogadro's number, 22.414, to find all the other properties of that compound. But so what we know now is we know a new way of finding moles, that we don't have to just do gas at STP, standard temperature and pressure. We can do gas at any pressure, at any temperature, because we can always get number of moles and then use that, right, to either find pressure, volume, or temperature, or use pressure, volume, and temperature to find number of moles. So basically what we're doing is we're finding a new way to get to here, or something new to do after we have moles of product. So we're going to do a few of these practice problems. So the first question says, how many moles of NH3, right? We always circle the do, are formed by the complete reaction of 2.5 liters of hydrogen gas at 381 Kelvin and 1.32 atm. Well, in order to get moles of NH3, I'm going to first try to find, well, how many moles of H2 have I reacted? And I'm going to do that using the PV equals nRT, the ideal gas law. So rearrange, that would be that the number of moles of gas is equal to PV over RT. So I have those numbers. I know that the pressure of the hydrogen gas is 1.32 atm. The volume is 2.5 liters. The R for atm is 0.0821 liters times atm over moles times Kelvin, and the temperature is 381 Kelvin, right? When I plug this into my calculator, I'm going to get a number, 0.105, right, moles, and that would be moles of hydrogen gas, right? Look at how the units cancel out. So the only unit that I didn't cancel out was mole. So now that I have moles of hydrogen gas, I can take that 0.105 moles of hydrogen gas, and I'm going to use the coefficients from the balanced chemical equation that tell us that for every 3 moles of hydrogen gas, I can make 2 moles of ammonia. And when I do that calculation, I get 0.07033 moles of NH3. And then obviously at the end of all my problems, I go back and I look at significant figures for the numbers that I used in there. And it looks like I'm going to need to round this number to 2 significant figures. Now remember, beginning zeros never count, but ending zeros count if they're after the decimal point. So that tells me that when I use 2.5 liters of hydrogen gas at 381 Kelvin and 1.32 atm, I can make 0.070 moles of NH3, which is ammonia. Okay, looking at the next question here, it tells me that it says how many liters of oxygen gas, so that's what I want to try and find, form when 294 grams of KClO3 completely react. Here's the reaction. And I'm given that the oxygen gas is at 755 millimeters of mercury and 305 Kelvin. So I have to think about what information do I have to start with. So I know that I have 294 grams of KClO3. And I can convert that to moles, right? I know that 1 mole of KClO3 from the periodic table would weigh 122.55 grams. And then according to the balanced chemical equation, that 2 moles of KClO3 would produce 3 moles of oxygen. So doing that calculation, I can figure out that I would make 3.59 moles of oxygen. But the question isn't asking me about the moles of oxygen, it's asking me about the liters of oxygen. So I know I can use PV equals nRT to convert from one to the other. If I want to find volume, right, liters is volume, I can divide both sides by pressure. So I know that in order to get volume, I need to take the number of moles, multiply it by the gas constant, multiply it by the temperature, divide it by the pressure. So the number of moles is that 3.59 number. The R is, because this is millimeters of mercury, I'm going to use the 62.36. The temperature is 305 Kelvin, and the pressure is 755 millimeters of mercury. Right? I look and see about my units. Moles cancel, millimeters of mercury cancel, Kelvin cancel. So the unit I will have will be in liters of oxygen gas. I get 90.65. And then I look back at all the numbers that I used, and they all have 3 significant figures. So that must mean that I can round my answer to 3 significant figures. So 90.7 liters of oxygen gas would be how much I would make. Okay, move on to the next one. See if you can do this one on your own. So press pause here, and then I'm going to go through the answer. So the question is asking how many grams of silver oxide are decomposed, and I'm given liters of oxygen, pressure of oxygen, and the temperature of the oxygen. So I know that PV equals nRT, and number of moles is going to be equal to PV over RT. So I can substitute in those numbers, 745 millimeters of mercury. The pressure is 4.58 liters. The R is again 62.36 liters dot millimeters of mercury over moles times Kelvin, and the temperature is 308 Kelvin. So when I do that, millimeters of mercury cancel, liters cancel, Kelvin cancel, and so I'm left with 0.1776 moles of oxygen gas. But the question is asking me about grams of silver oxide, so I need to relate those two. 0.1776 moles of oxygen gas, according to the balanced chemical equation, 1 mole of oxygen gas will require 2 moles of Ag2O, and then 1 mole of Ag2O has a mass of 231.8 grams. So now my moles of oxygen cancel, my moles of silver oxide cancel. I am putting that in my calculator, and I get 82.358 grams, and I'm going to round that to, looks like 3 significant figures. So my answer is going to come out to be 82.4, and that's grams of Ag2O. So this is just another way to do these stoichiometry problems. And we're also going to use this to sort of prove, where did that number come from? When we learned 22.414, when we were learning stoichiometry, I just gave you that number and said, this is true. Now we're going to really see why that's true, or mathematically how that works out. Remember what that tells us. right? That 22.414 liters is the volume of 1 mole of gas at STP. And STP is standard temperature, which is 0 degrees Celsius or 273 Kelvin, and pressure is 1 atm. So let's solve for this. Let's find out what will the volume be when 1 mole of gas, right? The pressure is 1 atm, so I'm going to use 0.0821 liters times atm over moles times Kelvin. My temperature is 273 Kelvin, and my pressure was 1 atm. And if I look at the units here, everything but liters cancels out, and I get 22.4133 liters. Let's say I use just 3 significant figures. That's how I would get 22.4 liters, right? So that is, in one way, the way that we know that that 22.414 number is true. That's also, by the way, how we figured out the gas constants. Like, where did those numbers come from? They were the numbers that were needed to make this sentence true.